thank you to the organizers for just really good themes and very good colleagues, and to Harrison for setting up this session. I thought I might use this time to say a little bit about the view of catalysis that comes from graph-theoretic methods we use to analyze the input-output characteristics of processes. And in connection to that, the particular role of catalysis in changing the structure and dynamics of the relevant entropies, which are responsible for the reason everything happens. I want to give you a mathematical point of view that has accumulated over the course of a variety of projects for several years at the various institutions that have been and continue to be my residence. Before things get too far out of hand, I want to thank the agencies that have sponsored different parts of this work across time, some of which still do. So I want to give you three general messages within this talk. We have colleagues, including some who are world-leading chemists, who do not like terms like network autocatalysis. For them, catalysis is what enzymes give to their substrates. They're okay with network autoamplification, they're okay with a lot of other terms, but not catalysis. So I want to start by being careful about what molecules and networks can do that have equivalent representations as being functionally catalytic, so it's clear what exactly we mean when we're saying this. Notwithstanding the fact that there are some functional equivalences, the kinds of effects that we often get from molecular catalysis tend to be of one kind, and I want to illustrate that they can change which entropies matter for a system, and in particular, they can move systems from the more thermal domains that we think of in physics to domains that are more explicitly computational, where concepts like algorithm become relevant to understanding why things happen, and of course, this is often where we find ourselves in biology. In contrast, when we find catalysis by networks or autocatalysis, it often is serving a somewhat different function. It can be a concentrating mechanism that allows hierarchy to form by simplifying inference problems, or it can be a source for structure in a collection of non-equilibrium entropies that allow things like dynamical phase transitions. And this is, of course, how major transitions can occur or how they can be robust. So, even though this session is called Theory and Computation, the rules of humanity still apply, which is that you shouldn't use equations in talks because it's hard for people to read notation in a fast presentation. So I will try to do what I can with diagrammatics. A good diagrammatic will contain all the same information that an equation does, and this one does that. So all the examples I will use are examples of chemical reaction systems, and the key things that you need to represent to model a chemical reaction system at the coarse-grained level are the presence of species, which will be colored dots, and they'll have names. So these are kinds of molecules. You need reactions, which you can think of as transition states, and those will be dashed lines of various kinds. You need to know what combinations are the input to a reaction and which are its products. And if you want to understand why this is a necessary thing to give a separate name to, I'll recommend you to the work of Horn and Jackson and Martin Feinberg from chemical engineering in the 70s and 80s. This is a concept called a complex. It is the idea that A does not just go to C, but that only the combination of a particular A and a particular B are converted to the product 2 of C and 1 of D. And the thing that makes chemical reactions both rich in abstraction and expressive power and also difficult to analyze is that these conversions occur concurrently or not at all, and they occur in specific combinations which are called the stoichiometry of the reaction. We will indicate stoichiometry by how many lines connect a chemical species to the complex that is the reactant or product side of a reaction. So, the important mathematical ideas that lie behind the diagrammatic are the following. In chemistry, we often use a reaction schema. What on the input converts to what on the output. If I only care about properties of a system that could be understood from detailed balance, so they're controlled from Gibbs free energies of the molecules, I may not put a lot of structure on the reaction. The undirected link is just a bidirectional reaction. But of course, this is just mathematics. I can use any stochastic process I want and try to analyze it. And sometimes it's appropriate to give attention to the different half-reaction rate constants, K and K prime. And if I want to do that, I may indicate that the conversion is a pair of unidirectional reactions with different properties, and this is the way we would write it in a reaction schema. Reactions are characterized at the aggregate level by fluxes or currents, And the two important things are that a current is actually not only the net is important, but a current is the sum of two half-reaction rate currents, one up and one down, and their roles need to be understood independently. So these are the average effects of stochastic events going upward or going backward, and of course the currents determine on average the change in the concentrations. What I want to point out is that the stoichiometric coefficients, for instance the fact that we produce two of these, occur linearly in the relation between currents and concentrations, but they occur in the exponent for the mass action rate laws, and this is what gives you interesting properties of convexity or non-convexity that makes the systems challenging to analyze. In many cases, we may not wish to explicitly consider the conversion of all the species. We may want some of them environmentally buffered, like B and D, and if that's what we want, then we may wish to absorb the buffered concentrations in with the sort of physical constants to make effective rate constants so that we have a reduced reaction in which only the quantities that we explicitly consider are denoted. And so we can make a graphic representation of that in this way. So with that, we have enough machinery to get a coarse-grained description of what we mean by catalysis or autocatalysis. Starting with a simple literal molecular form, if I have A going to 2C in the presence of an enzyme, diagrammatically, the input to the reaction is the enzyme and the substrate. The output is the enzyme and the product. In the reaction schema, the important thing is that both the forward and the reverse rates are multiplied by the same enzyme concentration because it is neither consumed nor produced, and that makes the enzyme a control variable. Because this is a stoichiometric and concurrent system, if the concentration of E is 0, I have no catalyst, I can shut this reaction off. I can also upregulate it or downregulate it by changing the quantity of E. And of course, this is one of the things we often care about from catalysis, is the role of a small quantity of something as a control for the throughput properties of a system of arbitrarily large extent. Now, in other cases, I may have a network in which a certain set of reactions complete a cycle in some form. I'll show you more about this one. This is the ultimate core network of metabolism. Through a certain set of network reduction mechanisms that I'll show you just in sort of overview, we can reduce this network to get to what the point is, which is that a catalyst, this is oxaloacetic acid, but you can think of it as biomass, is converting a reductant, here H2, and a carbon source, CO2, to vinegar. The Italian and French cooks will be happy that the reason there is a biosphere on Earth is to convert CO2 to good vinegar, and water, which is the product that pulls oxygen out of the system and drives the reaction. Of course, in actual life, since as Yeats observed, things fall apart, the only way anything remains ordered is if there are reactions that will regenerate the catalyst from the product. These are called in biochemistry anaplerotic reactions. But from the standpoint of our diagram, they take the output and they convert it into the catalyst. We can do the same graph reduction we did before, and this becomes the network that you get. But if we wish to consider these as buffered species in the environment, we can reduce further. And if we're running this system near a steady state, so that the output lives in a fixed concentration relative to the catalyst, we can reduce it even more, so that you see that the essence of this is starting with biomass as an input and getting more biomass as an output from species that are in the environment and are considered buffered. So the reason I drag you through this is that at this level of abstraction, network catalysis is indistinguishable as a process phenomenon from molecular catalysis. So if I wish to treat them the same, this is the level of abstraction that makes that possible. So part one, catalysis in networks by the components of networks. What does it do? Why do we care? Okay, let me start with the entropy function for an uncatalyzed process in the form that you've all seen several times this week. Typically, there is some trajectory through the space that's called a reaction coordinate. There's some set of reactants, and then there's some motion of one component relative to another in some continuum variable. Often it's a nuclear center. We could also have a proton that's moving into or out of the field of one or another orbital or ligand. And there's a favorable state where the reactants will spend almost all their time. There's a maximally unfavorable state, which is the transition state. And then there's another favorable state, which is the product. The rate of the reaction is limited by the ability to get away from the most favorable states to less favorable states. Often what you will see is the limit on only getting to the top of the hill so that you can go to the other side But I want to point something out to you that will become important later. It's not just the top of the hill I care about, it's the whole hill. And the way you get to the top of the hill, which is improbable, is by having done several improbable things to get partway up the hill. If our reaction coordinate is a continuous variable, and it's governed by some stochastic differential equation, then the average rate of getting up or down the hill is the net of the rates for going up and the events that go up and the events that go down. But if you ask what is the log probability to get to some point some point x having started at a place like x naught, that is the integral of the log of the relative probability to go up or to go down. Now, if it's just a chemical system, you can integrate this, and this is just going to give you the usual Gibbs free energy to get to the hill. But when I show you in later slides that we can do this for anything, we can do it for population processes in biology, for banking, whatever you like, the formula remains the same and the concept of entropy remains the same. So I want you to realize that you already know this from equilibrium thermodynamics. How does a catalyst change this? Well, we often see the cartoon of a big hill that a catalyst converts to a little hill. But for many cases, that's a bit of a sleight of hand, because remember that the reaction coordinate is a trajectory through a high-dimensional space. Often what the catalyst is doing is replacing one reaction coordinate, which was the best you could do before, with a different reaction coordinate that's the best you can do after. And of course, the reason this is possible is that the catalyst adds dimensions to the process. So consider, for instance, acyl substitution by a nucleophilic attack, which is acid catalyzed. So what we're going to do is we're going to take some group, like an acid group here, which we want to add, and we'll do that at the expense of displacing an equivalent acid group over here. If we wanted to do this without the presence of a proton, we would actually have to move electron density off of a carbon onto an oxygen, which is exactly where it really doesn't want to go. And we would have this big hill that we would have to accumulate thermal fluctuations to get over. The reason an acid can catalyze this is that you have a positive charge, which is available in a charge compensating hydration shell in the solution. When that is donated here, you create an overall positively charged system. And now there's a kind of an equilibrium sloshing motion that electron density can make between being carried on this bond in the hydroxyl group through to the bond here. The proton can change places, allowing it to move to the bond here, allowing it, after X leaves, to come back onto this hydroxyl, after which you give the proton back. So in fact, what we have done is, instead of having to go over the hill by creating net charge, we've created a situation where there's positive charge somewhere, and it's flat whether you move it from here to there or to there. And of course, this is the same thing that this is seen already from a famous concept in the theory of money called the failure of the double coincidence of wants. Why do we need money when we don't eat it or live in it or wear it as shoes? Well, it's because there often are people who want to trade things that don't exist in binary pairs. So the bank lends you money that's not intrinsically valuable, but it makes a bunch of binary exchanges possible, which after they have been completed leave everybody happier, and you can return the money to the bank. So what this does is it changes the time scales and the domains that can be accessed within your reaction system. I want to give you just kind of an everyday visceral feel for this. The seemingly fragile ester bond between DNA residues that give our sequence information can last for at least 14,000 years in a dry cave in human feces. This was 2008. I think there probably are larger numbers from South America now. If I put all of this complicated DNA polymerase machinery against the same molecule, I can turn over these base bonds in about a second. So there's a factor of 10 to the 10 difference. The point I want to make to you is that the chemical world is big. Covalent bonds stand like walls between different dimensions of chemical space, and in the absence of a catalyst, you don't get through those walls for tens of thousands of years. The catalyst is like a kind of a moving portal that allows you to go from one dimension to another. And I can't easily show you something in science that does this. These are common, popular from science fiction. And I assure you, for those of you who know him, that any similarity between Eske Willerslev and a character from Marvel Comics is purely incidental. But what does it mean for chemical space to be big? I didn't have a good example of how a catalyst opens dimensions, but kind of coming back to a conversation that Joel was having with us in the session yesterday, there's a notion of an anti-catalyst, which would be a mask that cuts off dimensions in reaction space. So an example of that would be the very famous Formose network, which is a way that you can get sugars by starting from formaldehyde as your main feedstock and glycolaldehyde as a little seed. This has been known since Butlerov in, I think, the late 19th century. If you put these guys together, sugars are very rich in hydroxyl groups, you get aldol reactions everywhere, and you make a big complicated caramel that no one can analyze, and in fact it has infinitely many species to it. A little subset of these, this is the work of Jakob Andersson, our colleague, formalizing all this in graph grammar terms, a little subset of these is the whole green plus blue network here. But of course, the people who want to understand origin of life don't want caramel, they want ribose. So Steve Benner, in this paper with first author Ricardo in 2004, recognized that borate happens to have the correct spacing, that it will disallow most of the reactions in this system and make a mask in which much of your product is directed toward ribose or arabinose. So you can think of what a catalyst does as the inverse of what a mask does. It takes these as the only dimensions you could have gotten them to and suddenly opens up this much bigger space. But a thing to appreciate, one slide from now, sort of the ultimate catalyst is this massive machinery in the translation system. You can think of it as living in a domain where there are charged amino acids that are capable of being polymerized. And there's this vast machinery, the 2 megadalton ribosome, the tRNAs, the whole ecosystem of aminoacyl tRNA synthetases that mediate the conversion of these activated amino acids in the presence of a messenger RNA into exactly one sequence of peptides and not anything else. So that door is completely closed except for one peptide. And in fact, in the very ancient days, there were people who liked to refer to genes as catalysts for the formation of proteins. This is kind of a big boundary condition for there to merely be a catalyst in. But the point that I want to make is, in the thermal domain that we discussed earlier, the problem of getting over the hill was a multiplicative problem where you have to get to one improbable place and then get to the next even more improbable place by a sequence of product events. In this domain, the entropy problem is instead a combinatorial problem. And it's a combinatorial problem of many kinds. So one combinatorial entropy is you have to have the sequence control to build all of this catalytic machinery. But then you also have to coordinate the catalysts and the substrates in the cytosol, which is an arrangement problem. For biopolymers, the synthetic cost is something that we can see in the cost of polymerization, which is paid for with ATP or other nucleoside triphosphates, with various reductants, NAD or NADP, and reduced ferridoxins, and so forth. But part of the polymerization free energy is what eliminates the sequence entropy. I will show you an example. For coordination, an example that the cell is willing to spend money for things that would eventually happen randomly is that you have these big, complicated GTPase proteins, the elongation factors, the initiation factors. Their job is to get activated tRNAs to the right place in the ribosome, or the components of the ribosome in connection to each other. Even though those can happen spontaneously, you're willing to burn a GTP per attached amino acid to make them happen faster. So the thing I want to illustrate with an example now is that the energetic cost of coordination entropies live in a more computational or informational domain of thermodynamics than the Hill domain. So here's a little model system that we can do exactly to illustrate. Suppose you ask, what is the least cost that you could pay to convert a random sequence to a particular sequence? Since if the machinery of polymerization were to run without being interlocked with a messenger RNA, you would synthesize random, unpredictable sequences. Well, so take a particular sequence. Vector alpha has some set of letters in order, and denote the polymer. This is a chemical name made with sequence alpha. The reaction schema for building that polymer is that you take some number of ATPs you're going to burn. You take the monomers of letter alpha in that you want to consume. You're going to produce the hydrolysis products, and you're going to build this polymer. At equilibrium, there is some reaction rate constant between the activity product for the ATP-ADP system or the AMP system in this case, because it's an adenylate, and then the activities of your monomers and your polymer. The thing I will care about is that the log of this whole equation is actually a statement that the chemical potentials of the inputs and the outputs must be the same, or the chemical potentials of the conversions, polymer to monomer and ATP to AMP, will balance. That defines the equilibrium condition. So now, I wish I were following the laws of humanity, but for the next slide or two, I will only half follow them. You can actually analyze what the least cost you can pay is using a lovely old concept from, I don't know, late 19th century, early 20th century, called the Van 't Hoff reaction box. Suppose I had a reversible ribosome and I were driving polymerization and depolymerization only by changing the activities of the ATP and AMP and pyrophosphate that drive the system. Then I could put one polymer in here and I could have a reversible ribosome that will convert the sequence into monomers if I push on this lever here and I pull ATP out of the system and put AMP into it. So I'm actually burning up the free energy in my polymer to replenish the ATP I'm pulling out of the system. Then I close this valve and then I push the other way. So I force polymerization, but now I'm going to open the valve for polymer A and I'm going to let my reversible ribosome push polymer A in. Well, you can make a diagram of this. Any of you who ever studied engines in elementary thermodynamics recognize that this is exactly the same kind of diagram as you make in temperature and entropy for a minimal heat engine, except now what we're going to do is the chemical potential. This is dead. Maybe we can do better. Okay. Our coordinates here, instead of pressure, are the chemical potential, and our coordinates here, instead of the energy exchanged, are just the number displaced along the reaction coordinate of the reaction. And so what you'll do is you'll match reaction conditions, you'll pull polymer into the system in whichever one is less favorable, you'll move to new reaction conditions and push polymer out of the system in whichever one is more favorable, whichever one is less favorable. And we'll do this in such a way that we return the number of monomers in the ATP to their original condition, so it's just like any other engine. And you can compute what the work is, the chemical work that would be needed around this cycle, and of course it's just the change in Gibbs free energy of one polymer relative to another. But now I want to show you something that will allow us to match this to a different problem. This is the same problem as before, but sparing you the algebra, which I assure you is fascinating. If you care, you'll be fascinated, and if you don't, you will be spared. But we can convert exactly the same expression for the chemical work performed into something that scales with just how many polymers you're converting, how many I take out of one sequence and put into the other, and then the integral of what is called a relative entropy. So this is like a Shannon entropy, except that the probabilities are not measured in some a priori space. They are measured relative to the density that you would have in the chemical equilibrium distribution at the free energies for the polymers you have. So in fact, you realize that there's a natural measure that chemical equilibrium provides, and the amount of chemical work that you have to do to convert one thing into another is just the area inside this curve, which is how far you are pushing the system away from its natural measure. But of course, we understand that any free energy is a combination of the internal energy that you're putting into the system or the boundary conditions. Those are the Gibbs factors that give you how hard it is to make a given state, and an entropy term, which is the sequence entropy, plus whatever other entropies of solution you have. And I can draw exactly the same cycle here in a space where I have 3 entropy coordinates. This is a kind of a simplex that you're looking at into the origin. There's the entropy of my whole sequence library, how many A's and how many B's. There's the entropy in the reactor, which we're going to return to its original value around a cycle. And there's the entropy in the heat bath, which is what we use to change the entropy in the sequences. And this same cycle, you realize, is being used to take entropy out of our sequence library and put it into the heat bath, or going the other way, to take it out of the heat bath and doing chemical work to put it into the sequence library. So you say, okay, why should I care? Well, here's a slightly different thing that looks very similar, and it's actually the same thing. Suppose I wanted to build a computer. I had a logical operation that was the basis of what I want to do, such as the computation of exclusive OR. I have two data streams that will give me two variables, x1 or x2. They can take a variety of values. And I will rotate them into my computational hardware. It can be shown, I won't show it here, that by a reversible process, I can transform any of these combinations into the answer I want for my exclusive OR, and something else that allows me to uniquely associate inputs with these outputs. But I don't care about this. This is not the answer I was asking for. So in order to reset the computer so I can use it on the next input, I have to get rid of the randomness in this waste bit. And the only way I can do that is by doing some work which then causes me to reject heat to the environment, because what work did is buy me enough state space in the environment that I can get rid of state space that I'm using in my computer. Okay, there's a famous analysis of this due to Rolf Landauer for the minimal cost of computation using this ideal gas computer that Leo Szilard had understood much earlier. The general idea is that the sequence entropy of the inputs, which is bigger than that of the output, equals the minimal amount of heat you have to reject to the world divided by kT, which is how much work you have to do to put that heat in. If I draw exactly the same cycle here in entropy coordinates like before, here's the sum of the sequence entropies for my inputs and my outputs. Here is the heat bath. Here is the internal state of the computer, which I have to drive through a cycle. Then in fact, what happens when I inhale data from my two input streams, I process it in the computer, I exhaust, well here what I'm going to do is I'm going to get rid of my waste bit, and then I'm going to exhaust my answer bit to the output stream. I've in fact just transferred entropy from sequence entropy to heat entropy. But this is the reason I showed you all of this. We started with this without catalysts. When we introduce catalysts, we introduce new dimensions to the system, which allow there to be flatter directions. But the important point, the reason I showed you the ribosome and the foremost network, is that we have to think of this not as one dimension going to two, but as a few dimensions going to an enormous number of dimensions. And it's in this enormous number of dimensions that all of a sudden the entropy problem becomes one of arrangement and organization. And for the analysis of that, we can make a term-by-term mapping, apart from little details of how the system works, between chemical problems like resequencing or positioning and computational problems such as logical reduction. So in fact, we have moved out of the thermal-looking world of cumulative probabilities into a more computational-looking world where the elementary things we have to pay for are more like logical operations. And so this is where concepts like algorithm become relevant to the kinds of questions we care about. So that was in networks. How about by networks? Well, the important rate equation of autocatalysis, which is the reason origin of life people like to think about it. Let me take the simplest example for which I showed you this little model before. I have some concentration. The forward reaction is to produce 2 from 1. The backward reaction is to produce 1 from 2. Equilibrium constant is this guy. If I write down the equation of motion for this in isolation, you can see, like on the slide long ago, the role of the network catalyst. It makes both the forward and the backward reaction faster in proportion to how much there is, but it's an auto-catalyst because the thing you're producing is in fact the same as the catalyst. The solution to this, of course, is exactly solvable. It's a sigmoidal growth curve, and your rate constant determines how fast the growth is, and your equilibrium constant determines where it saturates. So the important, without digressing too much, we don't care about these things in isolation. We care about how they can drive systems in the presence of other perturbing effects. This is why the only way to retain order in a dynamical system is to constantly rebuild against the falling apart of things. So the point I want to show you is that network autocatalysis and carbon fixation, there's empirical evidence to think this is the original constraint on biochemistry. It is not a clean argument, but it's the best I can do. When people want to make snarky comments that evolution has introduced so much wonderful complexity, we should no longer try to reason, we need to just memorize. They put up this picture of the reference reactome of the human genome from Kegg. I don't buy that because, and there are people who are not snarky, even sometimes me, but you can see here in the center there's a little cycle. And that cycle is not in the center. That cycle is the center. That's the 11 compounds in the citric acid cycle here. All biosynthesis starts from intermediates in this cycle. The smallest of them is our hero molecule vinegar, again, acetic acid. The biggest one is citric acid, has 6 carbons. So this is the network representation of that cycle that I showed you before. In fact, there are now 6 carbon fixation cycles known. All of them are network autocatalytic, but some of them go through networks that are off to the side, that's the Calvin cycle, or through networks with very complicated intermediates, the cofactors that are used in the Woodley-Ungdahl pathway. 4 of them are simple cycles through organic acids, and in fact, they all overlap with or are closely aligned with the citric acid cycle, and they always feed back into the citric acid cycle to make the precursors for biosynthesis. So I promised you, for a physicist, 11 is a large number, so you don't ever want to analyze something that has 11 of something in it. So what we would like to do is reduce this network to a simpler representation that gets to the essence. We can do this in the same way as you can reduce steady state throughput properties in Michaelis-Menten kinetics, for instance. If I have a pair of reactions that are back-to-back like this, that have inputs and outputs in complicated places, I don't really need to solve for x if I know what x is in terms of the input and the output to either side of it. So you can do some algebra and you can show that I can reduce this network both graphically and algebraically to a network that has this structure of inputs and outputs and effective rate constants that live here that look much like the Hill constants that you have in a Michaelis-Menten representation of an enzyme. So if I do that with our citric acid cycle model, it's a little bit like plucking strands out of a spider web in the rain or when dust blows through. I can take these guys out easily and I get to something that looks more sparse, but this is just hydration, dehydration. I can take that out, plink, plink, I get something even lower. And I can take finally all of these little yellow ones out, and this gets us to the diagram that I showed you on the first page. The effective equation that comes from these reductions of the rate constants is in fact none other than the equation that we had before, in which you can see that what's driving the system is the amount of forcing. I've written this as the Gibbs equilibrium distribution that acetate would have in equilibrium with H2 and CO2 against water versus the amount there actually is. If you could make more of it than you do, you push the reaction forward. And the catalyst for it is in fact just the amount of oxaloacetate which is being produced through quasi-equilibrium relation with the output of your reaction. So getting to the point that I tried to jump the gun on earlier, we don't care about autocatalysis in isolation. We care about it in the context of dissipative systems. So what you want to know is how hard you can drive the system against things that will drain your output to dissipation or to breakdown, and in which there may also be sideways, very slowly of getting to the same thing, but not fast enough to drain them. And the important point is that here you can get a phase transition. If you can't provide them by other means fast enough to overcome the drain, if you don't have enough to do it by autocatalysis, you may not be able to hold anything at all. But if you do have enough by autocatalysis, you can saturate your system. Meanwhile, if you're somewhere on the threshold, which is where we think of very early life, if you have autocatalysis, even if it's not enough to be self-sustaining, it can make the intermediates in your cycle preferred relative to the things that are available around the side. So, for those of you who have studied systems theory, there's a famous argument due to Herb Simon that if you find a complex system in the world and you want to know how it got there, you should prefer paths by which there were intermediate assembled components that had some stability. So Alexander's empire was not possible until large states could already manage their own affairs. And when it fell apart, it didn't become one person at a time in Central Asia. It went back to the management units before. That's why we want these small autocatalytic systems deep in biochemistry. And the last point, about which I won't be able to say much, is just that for non-equilibrium systems, like a system that has an uncatalyzed and a self-catalyzed reaction, you have positive and negative rates in the world of events, just like you do for escapes in equilibrium. And in fact, you can define effective potentials, which are entropy functions, but they're not Gibbs equilibrium entropy functions. And you can have multi-stability and phase transitions when these are non-convex. And it is the catalysis that makes this non-convexity possible. So phase transitions and dynamical systems are brought about in that way. So I am out of time. I would rather let people ask a question or two than read the summary comments since they're up here. Thank you.
All right, we're running into lunchtime, so maybe we'll only have one or two quick questions, then we can discuss more with Eric later if you have other questions.
I always admire the way you have very general concepts going across very different physical things. And one thing I was wondering is when you reduce the graph network of the TCA into the very simple case, in the RTCA or TCA, it became very simple, but is there a constraint? Is there, for example, would there be a network where you cannot reduce?
Yeah. Super question. I don't know the answer. I looked for the answer to that in doing this. The reduction I showed you was as far as I could do this and have the rate constant still expressed only in terms of buffered species.
Right.
If I had tried to reduce any further, I would have wound up needing to take things that were explicit in the dynamics and somehow absorb them into rate constants that I was trying not to make dynamical. Mm-hmm. I don't know what the general answer to that question is, and I would love to know.
I should have been more direct. So, for example, the RTCA has a cycle loop, and then there's the acetate thing.
Right.
But sometimes different organisms have different interconnecting, across the cycle.
Right.
And I was wondering if there are such cycles, would it still be possible to reduce into the form that you showed us today, or would it change? Would it qualitatively change?
I don't feel safe making general statements.
Okay.
Because the types of things that can happen in networks are so diverse. I think we have to have a typology of which classes can be considered sensibly the same. And then we want to be able to make statements at the class by class level. Okay. Little enough work of this kind has been done that I don't know what exists in the world of typology. This may be a thing where Nathaniel knows some work that's been done on this from chemical somethings. What is Peter Dietrich's name? Chemical organizations? Chemical organizations. I couldn't think of the term. So there are people who I think are interested in typologies of reaction systems, understood at the network level. They may have done work that addresses the question, how many classes can you coarse grain to before you start to lose essential information?
Maybe we'll do one more question?
Yeah, not that directly answers it.
Sorry. I'm not aware of work that completely directly answers that question. I would actually need to know exactly what the reduction rules are anyway, which you didn't have time to explain. There is another expert on. There isn't an actual expert on chemical organization theory here somewhere.
Right behind you.
Yeah. Yeah.
No, but yeah. Now that I have the chance, awesome talk. I'm impressed. And yeah, I prefer that we discuss it later on lunch because yes, there are things that we can discuss, but I'm a little yet just understanding all the chemistry behind because I only see A, B, C things, and I don't feel like I could say something more precise about the species, like the chemical part of it. So yes, let's have a discussion. Thank you.
Any other last minute question? Yeah.
Just back one slide. The graph.
Yes.
It's like a physicist. What are the axes here?
I apologize.
And their units and their directions.
People who speak within their time do a better job presenting their slides.
Fair enough. And it's
very
not
close
integer in this case. It's a continuum variable, right? So
very close to the beginning, I showed you that for the simple problem of escapes in transition state theory, as Henry Eyring first worked it out, the probability of reaching any point in the reaction, the log probability, can be written as a certain integral.
correct. Yeah.
This winds up being the log probability to take configuration n where n is the number of molecules in this system.
Okay.
And in fact, there is a whole first passage theory, which exists not only in low dimensions, but also in high dimensions. There's a stochastic process version of it, known as Friedland-Wenzel theory, and then many others that we can talk about offline.
Okay. So the wells there are like an initial or two states of the system that are metastable, perhaps, or stable under some conditions of temperature.
They are metastable, precisely so. And in fact, if you have finite particle numbers so that there's a probability of switching between them,
Yeah.
that finite particle number scales this whole integral, and the relative depth of these guys is the duty cycle, the fraction of time that you'll spend typically in each of the two states, just as in equilibrium.
Okay, I see. And so,
Yep.
Okay. Thank you.
All right, Eric's given us a lot to unpack, so I'm sure people will want to pepper him with questions later. But for now, let's break for lunch. We'll be back here at 1:30, and let's thank our speakers one more time.